So I forgot to mention it and I fixed it just now. I put the 2 in there, but I forgot that there's also a 2 in here. I'm going to be talking about how to do the chain and implicit differentiation. So when you're doing a chain, you also have to take into account the product law. Initially, we have 3 moving down as a product here, and we minus 1 from the exponent, we get 2 here. And that's the derivative of the outside. And the derivative of the inside is just finding the derivative of cos, which is negative sine. And there's a chain within a chain here, so we don't do the derivative here until this step. So now we do the derivative of this inside function, and that just ends up being 3. Once I've done this, I can multiply the 3's and add this negative 1 here, and we get negative 9 cos squared. Because of the 2, I can just move it down there. It doesn't matter if it's on the outside or the inside. And then the inside the same, 3x plus 1, multiplied by sine 3x plus 1. Now I'm going to show you implicit differentiation. So when you're doing it with polynomials and rationals, it's a little bit easier, but you still have the problem of getting square roots if you try and isolate for y. The same problem with trig here is that you can't isolate y easily at all, so we have to do a chain law in order to get it alone. And once again, when we're finding the derivative with implicit, we're actually finding dy dx, which is the derivative of y in terms of x. So we start off here, the derivative of 2 is 0, of x is just 1, and the derivative of negative cos is sine, because remember, of cos is negative sine, so you just switch the signs around here. The inside stays the same, and we multiply by the inside, which is, it would be 2 times 1, but since we're finding it, the derivative of y in terms of x, we need to put dy dx whenever we find the derivative of y. So we have 2 dy dx, and this is just multiplied with this here, so we can move the 1 over and get a negative 1. Now we can divide by sine 2y on the bottom and by this 2, and we get negative 1 over 2 sine 2y is equal to dy dx. We're going to be starting something called critical values, and this is really crucial for later on when we're doing curve sketching. Basically, critical values are the points on the graphs that are most important. They can really mean nothing depending on what happens in your critical value and sign analysis, but they can also be a min and a max, and that's what I'm going to be showing you guys how to do. So we have the function 2x squared minus 8x plus 1, and it's within the restrictions 0 and 3, where x can be equal to both of them. First of all, you want to find the derivative of your function. So the derivative of this is 4x minus 8, and you can just find this one using the simple power law. And now we're going to be actually jumping into the critical values part, which is something we haven't done before. In order to find the critical values, you need to find, first of all, when your derivative is equal to 0 and when your derivative doesn't exist. To find when your derivative is equal to 0, you make 0 equal to your numerator. In this case, you isolate for x and you find that x equals 2. In order to find when it doesn't exist, you have to find when the denominator is equal to 0. In this case, 1 is the denominator, so there really isn't even a need to do calculations because 1 will never be 0, meaning that this critical value doesn't exist. So our only critical value here within this restriction is 2. Now when we're doing sign analysis, we talked about this earlier when we're finding when functions are greater than or smaller than 0. This is exactly what we were doing before, but now with a derivative. So you have the sign analysis of your derivative between 0 and 3, and we put the critical value right in the center. We find here, we plug into 1 into the derivative, not the original function, and we find that it's a negative and a positive when we plug in about 2.5 or anything between 2 and 3. Since it was decreasing then increasing, we know that this is a minimum because f prime is smaller than 0 before, and then it turns positive after 2. We can show this pictorially when we go into the graph here and we have the linear function. Our y-intercept is at negative 8, and we can see that before our critical value of 2, it's negative and it's under the graph, under the x-axis here. But when we want to see after 2, just like on our sign analysis, it's above 0, and that's how we know that it's negative then positive, and this is our critical value. And this is not actually the graph of our real function. The graph of our real function, once we graph it, we can see that it is a minimum at 2. Found critical values and finding the maximum and minimum of just a regular function, like a rational, but we haven't figured something out with trig. So I have the function here, which is cos of x, something really simple that you guys can understand. And I have the derivative, which is negative sine x. Once again, you can find this identity just on your formula sheet. I don't really want to explain how you get there because it's not necessary. We need to find the critical values like we have always. So we have when f prime of x is equal to 0, so our numerator, negative sine x is equal to 0 at 0. You can figure this out by looking on your big circle kind of graph that we talked about in Math 30 with trig. But once again, that's not Math 31, so I'm not really going to be going over that. And we have f prime of x doesn't exist. Since there's no denominator except for 1, 1 can never equal 0, which means that there is no critical value for when f of x doesn't exist. Now we can push this onto our sign analysis with our critical value of 0, and our graph is between negative infinity and infinity. I plugged in negative 1 and 1 into negative sine x, and I got positive negative, which makes this a max. And remember to put your proof that f prime is greater than 0, which changes into f prime is smaller than 0. And I also want to put this notation here where we have f prime of x is increasing from negative infinity to 0, and it's decreasing from 0 to positive infinity. We've talked about critical values and minimas and maximas, but we haven't talked about how that relates to usage and how we can use that in curve sketching, which is what we're doing now next. Curve sketching is just figuring out how to graphically draw a function without having to use your calculator. In this example here, we have something that your average student would not be able to just draw it if you gave this. They would try and find points, but it would be pretty much impossible to do it without having to rely on their calculator. So we have the function x squared plus 5x plus 6 over x minus 2. In order to find points on our graph that are important, we initially need to take a bunch of steps before we can even do our first derivative and find our critical values. First, I like to find the x-intercept and the y-intercept. We just set x as 0 and y as 0. And we can find here through x-intercepts that our x-intercept is -1 and -3, and the y-intercept is just -3. Once again, this is just a simple process where you factor the top, and those are your x-intercepts. And here you just simply plug in 0 and it gives you a number